Okay, welcome back. Janet, if you're here, why don't you go ahead and let's get your screen set up again, okay? So she can share her screen.
I think
I'll be sharing the slides for her.
yeah,
I'll
Kelvin's
do that,
doing
yeah.
it. Kelvin's doing it, so there's no issues with transmission of that.
So let's find out where you were. Are you going to want to start right here? Or are you going to?
Right here, yeah, this is it. And let me go through quickly. Going back now, we were understanding how to map using potential field models from the ecliptic plane back to the open field regions. The potential field source surface model suggests should be there. And so on the left, you just see a couple of the standard maps with mappings to a few latitudes around the ecliptic plane. And on the right, you see a superposition of color-coded by magnetic polarity ecliptic plane footpoints that are mapped back to that coronal hole picture that we saw earlier. So that basically shows you where, within the model realization, the ecliptic plane solar wind magnetic polarity comes from on the sun. And you can see it traces out, in many cases, either the boundaries of the polar holes during solar minimum, especially, or low latitude holes. A lot of the ecliptic solar wind comes from low latitudes throughout a good portion of the solar cycle. Those first three panels are about a solar cycle long, and then the solar cycle gets a little more extended in the last two panels.
Janet, I think you might have just muted yourself accidentally.
Sorry. This is a bit of a hint of how to map back to the sun to get an idea of where the solar wind is coming from in the ecliptic, and a test of that is the solar wind polarity. On the next slide, there's a plot that goes from this kind of picture of mapping back to the sun to the Carrington day versus Carrington rotation picture, which is the ecliptic view of what that mapped polarity should look like. And on the next slide, I believe, is a comparison with Omni data, which shows without any account made for the 4-day or so transit time of the solar wind, how the structure in BR, the radial component of the solar wind in Omni, matches the potential field source surface equatorial plane mapping. And you can see, especially in the lower panels, that there really is a pretty good correspondence between the polarity predicted by the potential field models and the synoptic maps of the magnetic field used as their boundary and the Omni radial field. So that gives you confidence that the mappings are to first order roughly correct. So the next slide gives you an idea of where different latitudes map to on the ecliptic plane. What you have on the left is those footprints on the sun of the ecliptic plane field lines, color-coded by their latitudes, with the yellow being less than 10 degrees, the red being less than 20 degrees, and so forth, and the blue being the most poleward of the foot points. And on the right, you see the ecliptic plane version of that in the Carrington day versus Carrington rotation plot. And you can see that things change with solar cycle phase as far as where your solar wind is coming from. And I found it somewhat surprising that these panels start at solar minimum, basically, and that solar wind is coming from low latitudes. It's not coming from the polar regions, except right at the end of the solar minimum in these mappings. And you can see there's a transition in the color code from in the right panel from low latitude mappings. As you get into the solar maximum, you get into the mid latitude polar hole extensions, and then and the polar coronal hole edges in blue. And then as you decline back into the minimum on the right side of those panels, you go through the lower mid latitudes and then finally back to the low latitude source regions. So where your solar wind is coming from is not necessarily where you intuitively would expect with this dipolar coronal picture. Low latitudes are very important, and we really need to understand these low latitude coronal holes and what controls them. Next, please. And these are just a couple of Omni plots reminding us that the magnetic field structure, the polarity plot on the left, and the velocity plot on the right show a correspondence. So those high-speed streams in red on the right are really related in many ways to the way the magnetic field is behaving on the left. Once again, these are all ecliptic views of what's going on in the solar wind. Next, please. The next is, I think, just the density counterpart, and you can see the density ridges following those polarity boundaries. Next, please. So the other thing to note is that the slopes of those features are not horizontal, which would be true if they were really co-rotating in quotes at the nominal Carrington rotation length of 27.3 days. Some of those high-speed stream features rotate or co-rotate, if you would like, faster than the Carrington rotation speed, and others co-rotate slower if they're sloping upward. The next slide shows this a little more graphically. So this is a sort of a reflection of how the high-speed streams are forming and evolving with time. And the other point here to be noted is that those high-speed streams far outlive any single coronal hole lifetime. And so that they are a long duration feature in many cases that are controlled by a combination of factors and a combination of coronal holes that give you the impression of a single light beam rotating. But that perhaps is not as true as we would like to believe. And to understand this, we need to look more globally someday at this whole picture of where these high speeds are coming from and how they evolve with time and how they switch from one hole to the next. Next, please. So once again, this is a reminder that there's this systematic shift of where the solar wind is coming from in latitude on the right. And we have to take that into account when we're looking at the solar, understand how our images of the sun are relating to what we see in the ecliptic plane. Next, please. So what have we learned? We've learned that the high-speed stream and CIR structure and recurrence differ significantly from cycle to cycle and with cycle phase. And it's related to each cycle's distinctive solar field evolution. And these high-speed streams outlast the lifetimes of individual coronal holes. And in order to understand them and their return cadences and sequences requires more work on our part in understanding their origins and mapping back from the ecliptic plane to where they come from on the sun, and watching the evolution of the actual structures that produce them in the aggregate. So these models are great for providing sort of a global that allows us to track these coronal and solar wind structures. Of course, these are just all potential field source surface pictures that we've looked at. We haven't done the mapping out to 1AU with Enlil or Euphoria or Corhel or any of the other models. And that would enhance our ability to understand the details of the structure in the ecliptic plane at 1AU. But I think these models also bring up the deeper questions of how these various flows that are coming out of the corona are interacting. Some of these coronal holes are rigidly rotating at different speeds than others. And so there must be a lot of interaction of structures that have different azimuthal speeds that we're not properly accounting for in our thinking and our modeling, that hopefully the Parker Solar Probe and Solar Orbiter probing of this region will enlighten us about. So that's all I have to say today. And thank you for listening.
Thank you so much, Janet. Excellent. Okay, so we have some time now to discuss Janet's talk as well as the other talks before the break, and then to have a broader discussion. And Kelvin, can I ask you to go ahead and put the Slido up? Let me just give folks an idea of how we're going to manage this discussion. So first, can I confirm that Janet and Nicola and Pete are all here and ready to answer questions, right? Is that
Yes.
Okay, great. I see. And I think I saw Pete join. Catherine or Kelvin, is that true? We've got all three of our speakers from the opening session?
Yes.
Excellent. Okay. So then what we'll do is on the Slido, and you all can see this on your own screen, but we're going to put it on here just for ease of discussion. Barbara is going to be bumping questions up to the top. I'll probably be asking people to ask the question themselves so we can have this more as a discussion. Meanwhile, if you want to ask a question or comment on something or a topic of discussion, you can also raise your hand. I'll be monitoring that. When you raise your hand, and keep your hand raised until you're completely done talking, Kelvin is going to unmute you and I will call on you and you can talk. So that's basically how it'll work. We'll be using the Slido to help organize the discussion, but there will be opportunities for people to just bring things up as we go, either through the Slido, which Barbara is monitoring, or by raising your hand. So hopefully that's clear. I'd like to start by having some of the discussion questions about the last two talks, Nicholas and Janice, and then we'll open it up a bit more and go back to some of the topics that Pete raised. So our first talk, a question here is from Zubair. And Zubair, if you're here, would you like to actually ask this question yourself? And what you need to do is raise your hand if you are here and want to ask it yourself, and then Kelvin's going to unmute you. And if I don't see you do it fairly quickly, there you are. Good. Go ahead, Zubair.
Hey, Zubair, you should be able to unmute.
Hello. Hello. I'm audible?
Yes, we hear you. Great.
Yeah. Okay. Thank you. I have actually several questions. First one is, what I want to ask is, in Nicholas' model, like especially Paradise model, especially these events explain the low energy particle acceleration event. So does it model able to explain the impulsive event like we observe in a heliosphere as well as at one viewpoint? And my second question is, what will happen for the high energy particles? Does this model fails to explain high energy particle modulation, or it has some limitation? And third question, what I am interested, actually I'm very interested to know that in the Paradise model, he has included lambda perpendicular, that means perpendicular diffusion coefficient of order of 10⁻⁴. That means which is very low. So what will happen when perpendicular diffusion coefficient increases gradually? And if the perpendicular diffusion coefficient increases, does the model able to explain the decreasing profile of the particles in the inner heliosphere as well as at 1 UV distance? Thank you.
Okay, thank you for your questions. Let me try and answer them. So the first question, if I understood correctly, that was relating to the impulsive electron events, if the model can explain those. So yeah, we can try to simulate them, of course, but one of the drawbacks of our current model is that the Euphoria model, so the solar wind model, it has actually its inner boundary located at 21.5 solar radii. So we don't really model using, for example, an other MHD code, what is happening inside the corona. And so for these impulsive events, I think it's important to capture the particle transport starting from the low corona onwards. So in that sense, it's currently not really possible to model these kind of events. And I think that also relates to your other question, your second question, I think, about the high energy particles. We can of course try to simulate this modulation that you mentioned, but so far we have not yet done that. We have tried to kind of in one of our studies we looked at if we can produce this reservoir effect that sometimes occurs after a gradual SAP event, where all intensity channels different energy channels show the different kind of decreasing trend. And there, one of the things that the simulations actually indicated is that if you have, for example, guiding center drifts included, then this effect will basically break this reservoir effect and this kind of particle modulation. And let me just open. The last question was about the, if I remember correctly, about the crossfield diffusion, right? So the crossfield diffusion in Paradise, yeah, we have actually done some different. So for this particular study that I've talked about, in the case of the CIR event, we have done simulations with different values of the perpendicular mean-free path, and so the one that I presented here was the one that gave the best agreement. Which also like reproduced this these two particle populations, one centered on the forward shock, one on the reverse compression wave. If you include crossfield diffusion, then these two particles, these two populations, they start mixing up into one large population. You cannot distinct them anymore. There is also a bit less efficient particle acceleration, and the onset and the stop times also don't agree that well anymore. And one of these issues is also like when you include crossfield diffusion, you should probably in some way also make it depend on the background plasma. So the crossfield diffusion is inside the CIR is probably different from outside the CIR, so that makes it more difficult to have a good description of this crossfield diffusion term. But it's very interesting to look at. So thank you very much for your question.
Thank you, Nicholas and Zubair. Okay, I'd actually like to go to Karin Muglak, who has her hand up, and I believe you can unmute. Karin, do you have a question about for Janet or Nicola or the high-speed streams?
Yeah, for the high-speed streams, I put this in Slido, but I don't know if it shows up because I'm anonymous there. Just a question for Janet. So, question is, why are the coronal holes rotating faster or slower? And is there any systematics to that?
Yeah, I think that part of it has to do with the differential rotation of the photospheric field that's controlling these structures. And in fact, when the low latitudes are rotating faster than the high latitudes on the sun by about 5 days. And so, when we see the high-speed streams returning faster than the nominal Carrington rotation rate, they tend to be coming from sources at low latitudes where the differential rotation is faster. And when we see them rotating slower than the nominal Carrington rotation rate, they seem to be coming from the higher latitude coronal hole extensions. So it may very well be related to the differential rotation of the photospheric field, which is controlling the geometry of these coronal holes. It's a very complicated thing, the way the corona rotates. And Neil Shealy has done a lot of work with the PFSS model and Yiming, but there's also been a lot of observational studies. There's structures that co-rotate at different regions or at different rates, and there's also structures that differentially rotate in the corona, and they're all mixed together. So it's not a clean answer to your question, but I think there is a relationship to the fact that there is a differential rotation of the photospheric field, and it apparently affects the large scale structures less than the small scale structures because of the large scale diffusion and convection that's also going on in the photosphere. It's a complicated story. I recommend looking at some of Neil Shealy's old papers on the rigid rotation of coronal holes to get a better feeling for it.
Okay, thanks.
Thank
Yeah.
you. And Ian, I don't know if you're on, but I think you might have a comment on the slopes that Janet's talking about in the solar wind and then the coronal hole sources. Are you available to comment?
Yeah, I am here. I was actually just writing a reply to that, and I agree entirely that differential rotation is a portion of what's going on here, if not the largest factor. Yes, coronal holes and all features rotate much more quickly at the equator. However, I think it's possible that Rossby waves can also cause coronal holes to rotate slightly different from the local differential rotation rates. I've been looking at that with Student and Mausumi Dipaki recently.
Thank you, Ian. You're going to present that data in a poster?
I am not presenting anything on differential rotation in this conference, but I will be showing lots of maps with coronal holes in my oral presentation today and my poster on Thursday.
Okay, thank you. Okay, next. What's next? You just had my question right there. Here we go. Janet, do you see, sorry, Noor, do you want to ask this question? Go ahead and you can unmute yourself, I think.
Sure. Hi, Janet. I guess I'm a little bit hopeful with this question, but I'm just curious. I guess the sample of solar cycle is too small probably to see trends, but I'm just curious. When you talked about cycles to cycle changes in the HSS and the CERs, do you see any trends there?
Yeah, certainly there's trends. If you look at the presentation, each strip is roughly a solar cycle long. And you can see that whereas each solar cycle seems to be unique in many respects, the way the mappings to the photosphere from the ecliptic plane behave is there's a systematic movement from consistent low latitude mappings during the beginning of solar minimum. And then you begin to start getting some coronal hole extension, polar coronal hole extension, and polar hole contributions as you proceed into solar maximum. And then through solar maximum, this is solar polar coronal hole extensions are pretty important because active regions tend to draw down those extensions. And then we fade back into low latitude dominance, even in the absence of active regions. So it's almost counterintuitive what's going on. It may be the ecliptic perspective that is odd. I think it probably would be valuable to look globally at this whole mapping picture rather than just with the ecliptic myopia. But there are systematic trends from cycle to cycle. The cycles differ like they do right now because of the weakness of the active regions and the weakness of the polar coronal holes, even more so. But the trends seem to be fairly consistent. So I think that's a good question, and the answer is yes. There definitely are trends. They need to be called out more clearly.
Thank you.
Yeah.
Thank you. And as Barbara was just pointing out, maybe we can put the Slido link again in the chat. Kelvin, I believe we had a few people just arrive. The Slido you're seeing on here, everybody can access. You don't need to set up an account, but you can, without setting up an account, you cannot be anonymous, which is helpful because then I can call on you and you can ask your question yourself. You can also raise your hand and be called on that way, but right now we're using the Slido to kind of organize the direction of the discussion. So the next question up is Nariaki, and Nariaki, if you would like to, raise your hand, then and keep your hand up, Kelvin will unmute or give you.
Nariaki kind of had a modification of the question, so please ask both of them, Nariaki.
Yes, and yes, there you go.
Can you hear me?
Yes, we can.
I'm just curious about the organization of the global magnetic field in terms of the polar field strength. What is the polar field strength? And in Wilcox observations since 1976, as Pete said, it captures like the field strength above 50, 60 degrees of something. But it's a big range of latitude. And how about more recent observations by namely IOHMI, maybe limiting to a latitude of 70 degrees. And of course, there's another question about the presence of patches of enhanced magnetic field, as first reported by Hinode observations. How does that contribute to the mean field as observed by longitudinal magnetographs like Wilcox or MDI? So those are my kind of naive questions. And I ask both Pete and David Hathaway to chime in if possible.
Yes, in fact, I was just going to say that. Let's Pete, why don't you go first, then we'll do David. And if others then want to comment on it also, they can raise their hand. But let's start with Pete. Go ahead, Pete.
Okay, so with respect to the Wilcox calculation of the polar fields, the reason that we look at those is because there's such a long baseline. So I agree that we would much rather use HMI or MDI observations, but there's a much shorter time span that we can look for trends. And as you know, as well as anybody else, you can't just stitch these magnetic maps together because there are systematic biases between one and the next, and there is no ground truth. So when we're looking at Wilcox, in fact, Todd doesn't actually put dimensions on his data sets because that's how I guess cautious he is about defining the strength of the field in terms of a quantitative measurement. So that would be one reason why we continue to look at Wilcox, and the reason it's down to 55 degrees is because the resolution is it's absolutely awful compared to more modern telescopes, which, like you say, maybe then you could go up to 70 degrees. Now, in terms of the Hinode observations, that's a great point. And as you know, when you're looking at a completely idealized dipole configuration, as you get towards the pole, that line of sight field basically disappears as the field is almost exclusively in the plane of the sky. So you can't see those flux bundles because of our Earth-centric view. So there's a geometric effect as well as you're going up to higher latitudes. So we've tried to statistically address that in the calculations by putting in some statistical flux bundles, and that actually seems to help. It seems to make the global model results give us a better response because that extra field tends to push down the field lines a little bit more. It tends to flatten the heliospheric current sheet slightly, and that all seemed. And then the streamers, when we can compare them with observations, which is difficult in its own right, they tend to be a little bit more consistent with the observations. So did that answer or did that address your two main comments?
Yes, but another question is, what's the difference between polar coronal hole and core holes and the equatorial coronal holes? In polar coronal holes, when they are dominant, we see lots of patches of strong magnetic field. But do we see them in equatorial magnetic field, among equatorial coronal holes? So are polar coronal holes the same as equatorial coronal holes? That's another my naive question.
That's a great question. I think I'd like to see if David Hathaway wants to comment on that or what you were just talking about, and then we can return to that. Go ahead, David. Raise your hand, David, if you're there. And you should be able, you should be able to unmute yourself if once Kelvin gives you that.
Go ahead, David.
Can you hear me now?
Yes.
All right. Yeah, I agree with what Pete said about Wilcox. It provides a long, uniform data set where they've taken particular attention to take into account scattered light in their measurements. The reason they do 55 degrees and higher is because that's their poleward pixel. One pixel covers 55 degrees and higher in their data. So, if you're using their data for polar fields, that's what you get. Of course, we do have other more detailed measurements, so far more detailed measurements where you can integrate over area from typically 75 degrees to the pole, but I'm not sure how much that changes. I prefer to use Wilcox just because of the length and uniformity of the data set.
Okay, and I see we have somebody who's raised their hand, Wai Wang. I'm not sure, can you identify, go ahead and unmute yourself and then also identify who you are, because we only see part of your name. And in fact, can you change your name so that it has the whole name? That's always better so people know.
Yeah, this is Yiming.
Oh, hi, Yiming.
From NRL. And I'd like to comment on the Hinode. Seeing Hinode saw these big clumps of unipolar flux at the poles. Well, that's exactly what you expect. I mean, because the flux is being concentrated at the supergranular vertices, the same exactly as what happens at unipolar regions at low latitudes. And I think it was that paper by the 2008, 2009 paper, they compared the polar hole or the polar fields with quiet regions. They should have compared it with unipolar regions at low latitudes. And if they had done that, they'd find it's very similar. I mean, you take of course, the polar field is strong. So you need a strong unipolar equatorial coronal hole to compare it with. And so that's my comment about the Hinode and the polar. So I don't think the structure of the polar fields is not that different from the structure of a strong unipolar region at low latitudes. And the second thing is the reason why Wilcox is useful, despite its low resolution, is if you're interested in large scale global field in the heliosphere, you don't need high resolution. The Wilcox, the last pixel going from 55 degrees to the pole is actually, it's adequate. You don't need very high resolution. And the main thing is, as David said, is you need stability, good 0 point, and capture the very low order multiples, dipole. So you can have very, very big pixels for that. You don't need very small, high resolution. Okay, that's all I wanted to say.
Thank you, Yiming. It's great. So let's go on to the next question that's up on the Slido from Claudia Nicoli. Claudia, if you want to raise your hand and keep it up, then Kelvin can unmute you and you can ask it if you're here.
She might not be in the session.
All right, then I'll just read it. Janet, and this follows on nicely from the last question. Oops, it just went away. Please, could you consider, what do you think was the most, it's okay. What are the most important difference between coronal holes, there it is, observed in 2008 versus the last solar minimum?
Oh, 2008. 2008 is sort of the stereo's solar minimum. The previous cycle had these very well-defined, long sweeping co-rotating interaction regions. And they had these slopes that suggested non-Carrington rotation regularity of recurrence, meaning that they were coming from different latitudes at different times. It's not quite so clean this time around. It's a messier situation, and it's not clear to me exactly how it will come out, but I don't see these long-lived sweeping streams lasting as long and being as well defined this time around. Somehow the multipolar structure of the solar field is very busy and not as organized as the previous very deep solar minimum. So I think the previous deep solar minimum was special. I agree with Pete that it was some special minimum, and that it bears study for that reason. But we may be going back to a more normal in quote state, except for the fact that the polar field is still weak. So every cycle we've seen has been different. The 2008 one is cleaner from the viewpoint of interpreting it, I believe. And so maybe we should always be mindful of the fact that we have that data when we're looking at the present cycle and do regular comparisons.
Thank you. Okay, Alberto, I see you have a question here. Do you want to go ahead and ask it?
Yeah, hi, can you hear me?
Yes, no bugs.
Okay, good. Thanks. Pete, in your talk, you showed PSI results for different rotations from different minima. In particular, the latest one was Carrington rotation 2224. I was just interested in knowing which boundary conditions you use for those simulations.
Yeah, we used HMI for the most recent ones, and before HMI data were available, typically we use MDI. But we also, we've run these calculations back many years. So the ones from WSM, I think they used Kip Peak, if I'm not mistaken.
Right. I guess my question was also related to the point of, are you guys using like the instruments synoptic products by themselves, or there is some extra processing on those synoptic magnetograms, like like AdaptGong or something like that?
Yes, so we do use the synoptic maps. We have played a little bit with using the disk images and trying to create them ourselves, but we're not the experts in that. So it makes more sense for us to use the synoptic maps, but you can't just stick those into the calculation, at least in the MHD calculations. You can get away with it with a potential field source surface solution because the algorithm's a lot more forgiving. So we have to smooth or diffuse the flux a little bit, and we also have to figure out what to do at the poles. And we've tried different things at the poles. Many years ago, our best estimate was to try to find the lowest order components of the field based on where we could observe the sun properly, fit those, and then extrapolate them. Now we are trying to keep as much of the original data there as we can, but also add in some extra flux based on these Hinode observations.
I see. Okay, thanks. Yeah, well, I will mention something about that in my talk. That's the point of my question. Thank you.
Okay, yeah, the last part is we are using the adapt maps, either based on Gong or HMI as well. So for the predictions we do for PSP, we use the adapt HMI maps, which seem to perform the best. And as you know, what you put in strongly influences what you get out. So
exactly, yeah. Thank you. Thank you so much.
Yeah.
So we have two more comments. They're not questions, but they're very good comments. And one is from Joan Burkbile concerning structure near the sun. And one is from Heather Elliott about the sun going further out. So my proposition is that we kick off the remainder of this discussion with letting Joan and Heather elaborate a little bit more on that. Does that sound good?
Yeah, it sounds good. And I think I'll actually take a moment, since we're kind of shifting a little bit. We've called these plenary discussions early in the week data and model assessment, and later in the week it's sort of a forging connections and collaborations. And so part of what we're doing with the scene setting and having these initial conversations is to highlight exactly the sort of thing that came up in the discussion with Pete and me and Joan about, just how dipolar, which minimum is like each other and what are we looking at. And it shows how we need to look at different data and different people need to talk to each other. And so right now we're kind of assessing what's out there. And so maybe even before we have Joan and Heather speak, Barbara, you can briefly comment on the hub that we're putting together to try to facilitate people knowing what other people have, basically. Can you make a comment about that now? Because
we'll give a better overview tomorrow. But so we have a challenge, which is that you have your interests, but the whole point of this is to really be able to combine data and models in a way that we can gain greater understanding from that. And so we have a couple of elements that we're putting in place. One of them is a hub. It's kind of like Amazon.com. You put in your entry, you have different features or parameters that you can attach to it. And then somebody searching that database can go through and either do text or they can filter it the way you would do with that. And so we're starting to put things in. We're still kind of refining the parameters in it, because I find we thought that we chose some straightforward things, but it turns out people have very different things that they're needing to share and give information on. And so that's in evolution, but I'll be working with all of you over the next, following this workshop, to make sure everything that needs to be in there is in there. There also is a Amazon cloud for WHPI, where we can not only host data sets and model products, but also interactive. If you have a Jupyter notebook that you can put in as an interactive notebook, it can host that too. You don't need an account on the cloud. It'll work through a browser. And so once we're done with this, once we start to decide on what our focus data sets are, I can start getting those online as well.
Okay, great. And I'll get to Heather in just one sec. Let's go ahead and let Joan comment on the discussion that came up earlier about the corona and the dipole nature, and we can see if anybody else has further comments. And then we'll talk to Heather about the outer heliosphere a little bit. Joan, are you available? If you are, raise your hand. Oh, there she is. Okay, so.
Yeah, can you hear me?
Yes, I can.
Yeah, so again, this is white light data from the ground at the very low corona. And it goes back, we have images back to 1980. And if I look at the minimum that took place in 86, we have the closed regions confined to very low low latitudes, so large coronal holes. We see a similar thing in 96, although the closed regions have slightly higher, they're extended a little more in latitude. And of course, in 2009, they were quite extended, and we never really saw a sort of a simple flattened dipole. But just looking at Mauna Loa, I have seen something closer to a flattened dipole in the K-core images. Not every day, but typically rotation after rotation, you see periods of rotation that have that. And I do need to put together the more recent minimum data and extend it for this 4 solar minimum just to quantify that. But with the other thing we saw in the previous, the minimum, the declining phase, preceding the minimum in 86, preceding the minimum in 96, we saw, apologies to Janet, but sort of a classic tilted dipole, because I know she was saying we have to get out of this idea of just thinking about tilted dipoles. But we did see a more classic tilted dipole that we did not see in the minimum leading up to around 2008, 2009. We never saw that. And then I did see that again starting in sort of 2016, 2017, 2018. I did see a tilted dipole again in this previous declining phase. I can't say I know what the cause of it is, but I do have a question, and that is, it was pointed out to me in the minimum in around 2008, 2009, there was a fair amount of mixed polarity in the polar hole regions. Is that mixed polarity sort of the same percentage as it was in the previous minimum? Does anybody know? Was there a significant amount of mixed polarity in the polar coronal holes?
I noticed that Yiming has his hand up. If Kelvin could let him unmute.
Sure.
Okay, go ahead.
Go ahead.
Yeah.
Yep.
Yeah, this is Yiming. I just want to make a general comment about the flatness, like the stream belt, how quiet the sun is at minimum, at different minima. Well, I think the most important thing to keep in mind is it takes about 1.5 years for active region flux to decay away. And at least the part of the active, what we call a non-axisymmetric part, that decays away in about 1.5 years. And the axisymmetric part just hangs around for much longer. So I think the difference in the flatness of the streamer belt and parameters like that has to do with how many, well, when was the last significant active region present, and how long did they have to decay? And basically what happens with active regions is the flux gets moved to higher latitudes by the meridional flow. And then at mid latitudes, there's very strong rotational shearing. The differential rotation is strong, and that accelerates the decay of the non-axisymmetric part. The axisymmetric part is not affected by the differential rotation, and that continues to go to the pole. So basically, you want to look at the last active regions of the cycle. How long have they had to decay? How many were they? And how large they were? And I think that will determine things like how much mixed polarity flux there is around, and how flat the stream belt is at different minima. That's all I want to say.
Okay, thank you. And Pete, I see you have your hand up.
Yeah, just to follow on from what Yiming said. So there's a relative balance between the large scale dipole field that you see in the polar regions, which is what I emphasized in my talk when I was making the comparison about the most recent minimum and the 2008 minimum being similar. But what I didn't mention was the relative contribution from mid-latitude active regions. And so if you look at the 2008, 2009 magnetograms and compare those with the 2019 magnetograms, there's a lot more structure at mid-latitudes from those active regions. And so I think it's that relative balance which might explain why the recent minimum had a structure that was more like, in white light, was more like the WSM interval.
Interesting. Anybody else have a comment? I see Joan still has her hand raised. Did you have another comment?
John, go ahead.
Sorry about that. No, I forgot to put my hand down. Sorry.
No problem. Yeah, you do want to keep it up for the whole time, but then take it down when you're done. Anybody else have comments on this subject? If not, let's actually, Heather, if you can comment on this about how things change going out.
Yeah, sure. Both the Voyager 2 solar wind observations and the New Horizons observation show significant decrease in the amplitude of the solar wind structures, like how variable the speed, the density, and temperature are. And it significantly decreases beyond 10. And New Horizons has been taking observations between, we have really good coverage beyond 20 when NASA allowed us to operate during hibernation. So between 20 and 50, we have good coverage, and we're covering that distance range from maximum down to minimum, but the maximum was a low maximum. And compared to Voyager 2, it's like typically like 100, so like the maximum for Voyager 2 and sunspot number was over 200, and the maximum for the cycle, where New Horizons was, just a little over 100, like maybe like 120 or 40 or something. So what this means is the New Horizons observations, we've been collecting some of the most quiet solar wind observations ever, because a lot of the structures have been worn down and merged by the time they reach New Horizons, and it has been a low activity cycle, and our observations go into solar minimum. So, we're seeing changes in speed for solar wind structures of like 5 and 10 kilometers per second, whereas in Voyager at the same distances might see a swing of 100 kilometers per second. So it's an interesting data set, and I'm going to be adding it to the data set collection for WHPI.
Does anybody have any comment or question about that? Okay, seeing none. Barbara, yes, okay, we answered. Let me actually bring back one question, which I think was active in the discussion, which is the question about the rays that Pete talked about. And you talked a little about this right afterwards. And there was some discussion about the three-dimensional effects of associating the remote sensing rays, for example, with the in situ. So Pete, did you see those comments? Craig made a comment. Or Craig, if you're on, do you want to actually make your comment live? Raise your hand if so. And there he is. Okay. I think
let's see.
We can.
This was I'm sorry, I've lost track of which one or which question we're on.
Yeah, sorry, I jumped back. Can you actually pop up the question? It was the question originally from me about the rays.
I was remarking about the rays and the fact that we've Anna in particular has had these great insights about the nature of coronal loops farther down, and the fact that they're not really compact along the line of sight. They may be very complicated veil-like structures. I'm increasingly of the opinion that that rays are probably that way too out in the corona. I know there's some discussion of that already in the literature, but I thought maybe we ought to comment on that here or discuss that here. Do you have any thoughts along those lines?
I think he's asking Pete.
Oh, so my naive interpretation, I think, Craig, you're probably much more qualified to address this, but the interesting thing about these rays is that because they're coming from the WHPI brightness observations, that they're so much closer to the sun that you're resolving stuff that we can't see from 1 AU. And so I think these are, these are the tips of streamer belts or pseudo streamers that we're seeing.
Sure. Yeah, I think we're going to end up finding out that, in fact, it's not necessarily the location as much as the signal to noise ratio that matters, right? A lot of the reason these are visible in WHPI is that WHPI is closer, and so it gets more photons from the rays. But beyond that, I agree with you that these look like
isn't it also a line of sight integration effect that as you get closer, you're actually sampling a much shorter interval along your line of sight?
Well, there we go. I'm going to step right into it here. WHPI has exactly half the line of sight integration problem as a regular chronograph. So it's not a huge boost to the signal to noise in itself. It's really a proximity effect, right? Because it still has to integrate through half the corona.
Yep. Okay.
And I see that Yiming has his hand up again. Would you like to comment?
Yes. I missed the earlier discussion about rays, but if you mean the, I mean, even from the very beginning with LASCO, if you apply an unsharp mask to the streamer belt, you see that the whole streamer belt is composed of rays. Well, we call them rays. And my interpretation of the rays is that they're product of the interchange reconnection. The streamer loops, the high streamer loops, are reconnecting with the open flux at the boundary of the polar holes at the edge of the streamers. And then through that interaction, you get a new open field line with closed field material streaming out along it. And that's your ray. And if that's the case, you would expect the rays typically to last, well, it's the transit time through the field of view. So it might be a day, and then you would expect it to fade away. But it was very hard to track individual rays, so we couldn't test that. So anyway, I'm not sure if that's what you meant by rays, but we did see rays from the very beginning of LASCO.
Pete or Craig, do you want to comment on that?
I'm trying to absorb it. That's really interesting. I'm thinking whether or not the WHPI observations could address that now. I'd have to look at some of the movies to see what the whether or not you could interpret a timescale for them, because I'd also been thinking about them differently in terms of your sampling through a larger coherent structure that's tilted. I think you mentioned that in one of your comments, Sarah. And that way you could get that without any reconnection going on. And in fact, the work that Poirier has done, their model isn't time dependent in the sense that they've got any reconnection driving these features, and they do see more broad rays that seem to match up well with the observations. Of course, the models can get the right answer for the wrong reasons. I don't know. That's very interesting, though.
I'll jump in here and point out this is at least the structural aspect of the question. I think we will eventually get a handle on with WHPI, right? Because it's got this changing viewpoint that we just don't have with any other coronagraph. I have a student, Megan Kenny at CU, who's working on doing exactly that, trying to do tomographic inversions of the vicinity of the spacecraft. So we expect to get some results on that sooner or later.
Great, thank you guys. We have a couple more minutes. Barbara, you had a comment, right?
Well, I thought, you know, I was impressed with the way Janet showed the solar wind data in a context that was comparable and could be followed from cycle to cycle. And I also had when Joan and Pete were talking and you were talking about dipole versus non-dipole structure. In the previous cycles, what we did is we made maps both on disk, but also off-limb maps. You can take an annulus of in a coronagraph and put that in a thing at different altitudes. And I thought those were kind of nice and valuable because that gave you a way to combine different types of data and look, but also look at how that evolved as a function of altitude. However, we started doing that in 1996, and now we're kind of coming into a more modern era. We've gotten better at data representation and more creative. And so as we move into the mosaic section next, what we would like to do is really find a way to take all this diverse types of data and you know, find a way to give context relative to each other so that as we go into a deeper dive into the analysis of our particular data sets, we do have some context to relate that to other things. And so the synoptic maps are kind of a nice baseline. I like to see the way that different people are representing things. But as we lead in the mosaic session, I'd like people to really challenge themselves to say, you know, what's a good way to represent this relative to another thing? Or what would be a nice combined data product that you've seen that you'd like to see us to do for WHPI? Because this workshop it doesn't end on Friday. The work really begins on Friday when we get to know each other's work, when we start to understand the deep science questions we're trying to answer. We want to move on into really building not just a mosaic of the different types of observations, but also a structure for us to do that science and do that collaborative work even more. And so I thought that was it was a good way to maybe lead off for the mosaic section. Unless Sarah, did you have any comments?
No, exactly. I think you've said it very well. And I think it's a great time now to hand off to our chairs of our next session, which is session 3, and those are Heather and Carlos. Are you guys here?
Yes, we're here.
Right, thank you.
Okay,
Yes.
thank you. Thank you, Barbara, for the introduction. I apologize for the background noise. There is some construction going on. I wasn't expecting that. So this is the way that it will go. This is the first focus topic for working group 1. So we have 3 talks, 10 minutes each. So we will leave the questions for the end of the talks. So Heather will be taking charge of the Slido. So please post your questions on Slido. And then we will have a discussion, the last 30 minutes of the session. So our first talk will be, Calvin, if you can share the slides, please. Here we are. Yes. So Ian, very appropriately, will be starting this session with the title, Sun Heliosphere Mosaic. Welcome to Solar Minimum 2425. Ian, go ahead.
Thank you very much, Carlos. And I want to thank all the participants. This is really a wonderful opportunity for us to all work together on this solar minimum. My name is Ian Hewins. I'm at High Altitude NCAR. And this is an introduction to the Sun Heliosphere Mosaic that we're going to be putting together. And a welcome to Solar Minimum 2425. I worked with Barbara Emery and Sarah Gibson on all of this, and you'll see more of this type of data from Barbara Emery. First of all, I just want to comment that you're going to see some things here that you saw Janet talking about, and let me begin. So there are many ways to look at the WHPI data, and a primary goal of the WHPI initiative is to build a mosaic of the system during minimum and make connections from the sun to Earth and throughout the heliosphere. Daily images of the sun itself being a good place to start, such as this SDO EUV image, are one way we can look at this data. This is an AIA 193 image, and that's one of our favorite coronal holes from this minimum. We call it Mr. T. It is a positive polarity coronal hole in the northern hemisphere that kind of lasts for a fairly long time. However, we can also look at solar wind data, such as this Omni plot that shows DST, BZ, and velocity. And we know these data are connected, so we just have to demonstrate how they're connected. And one of the ways we can do that is through using models. Models can really help show which part of the coronal magnetic field is open to the solar wind. This is a PFS model, a DeRosa PFSS model known as the hairy sun or hairy ball. And I just want to point out that the time and date is the same for the image on the left and the image at the center. So these positive polarity green open field lines you're seeing are actually originating from that coronal hole. So what we undertake is no small feat. There is a myriad of data for this minimum, as I said, and this SDO EUV data, AIA 193, this is just 1 year of one type of data for solar cycle 24 and 25. You can see there are recurring low latitude coronal holes. And I'd say that is the thing that characterizes this minimum the most, is a large number, and in some cases, large area low latitude coronal holes. So how do we rise to the challenge? One way to look at each rotation of the sun in its entirety is a synoptic or Carrington map. You've heard that term a number of times already, but this will help you understand exactly what it is, how it's put together, and what it looks like. A Carrington map is a form of projection used to flatten a sphere's surface into a plane. And although the resulting rectangular shape does create some distortion, particularly towards the poles, it remains one of the best ways to view and track feature evolution over time. So time tracks from right to left, beginning at 360 on the right and moving towards 0 longitude on the left. The equator is the horizontal central latitude lines, and the poles stretched out as they are, 90 degrees in the northern hemisphere and 90 degrees the southern hemisphere at the tops and bottoms of the maps. Coronal hole Carrington maps made with SDO EUV data allow us to focus on the dominant form of space weather during the minima, high-speed solar wind streams, connecting them to open field at the sun. Now, I'd just like to point out, this is a map made with SDO AIA data, 193 and 304. We also made Carrington type maps from the stereo A perspective, and you'll be seeing some of them shortly. Oops. And this is another way to apply the DeRosa PFSS software. You saw the hairy sun above, but it can also be applied to a Carrington map, tracing solar wind and its velocity back to its coronal hole origins. So the velocity, the red and yellows are the higher speeds, the blues, purples, and blacks are the lower speeds. So we're getting our high speed streams in this upper range. And the gold stars here represent the origin of the solar wind. You can see it jumps from the pole to the low latitude coronal holes, switching polarity and back to the pole in this case. That is fairly common throughout this minimum, that we have the polarity of the solar wind source switching and it moving from the pole to the low latitude coronal holes. Omnisolar wind data mapped back adds more information to the mosaic of the heliosphere, telling us how this solar wind interacted with the Earth's atmosphere. Now, when you map back, you can see that you're getting these peaks here roughly.
Ian, I think you're missing, I think it looks like maybe you're not advancing slides.
You're not seeing the solar
Yeah,
wind?
sorry.
We still see the sun.
We still see the sun. Yeah, what slide are you on?
Oh, no, I'm
sorry. You know, we're back on where the movie was of the unwrapping Carrington map. Sorry, I didn't catch it earlier.
That's very bizarre. I'm on many slides further along than that.
I thought you might be, yes. Can you jump out and jump in maybe?
Are you seeing my screen again?
Yes, you were frozen 2 slides up, so you might want us to go up to 7 and quickly hop through it so we see it.
Yeah, 7.
This one here?
We saw that, yes.
Saw that? Okay. All right, sorry about that. That's bizarre. Let me get back into full screen mode. All right. All right, so coronal hole Carrington maps made with SDO EUV data allow us to focus on the dominant form of space weather during the minima, high-speed solar wind streams, and connecting them to open field at the sun. Once again, this is an SDO AIA coronal hole map, Carrington map, or synoptic map. That's Mr. T again, our favorite coronal hole. We also made stereo A maps. Hopefully my slide just advanced and you're now seeing the PFSS at the lower left here. So you saw the hairy sun model earlier. This is also a DeRosa PFSS model, and it is being applied to this Carrington map, tracing the solar wind and its velocity back to its coronal hole origins. Red and oranges and yellows are the higher speed streams, the HSS, and then the lower ones down in the purples and blacks. And you can see that the source is at the gold stars here, and it moves from the polar coronal hole, positive polarity polar coronal hole, to this low latitude positive polarity coronal hole. That's Mr. T there, back to the pole, and then down to these negative polarity coronal holes. Omnisolar wind data mapped back adds more information to the mosaic of the heliosphere, telling us how this solar wind interacted with the Earth's atmosphere. And you can see these peaks here in this map back line up with the large low latitude coronal hole here, although there is fluctuation throughout that returns again to the low latitude. More results like this will be presented by Barbara Emery in her HSS presentation and also by me in my poster on Thursday.
1 minute.
So what do we mean by the WHPI mosaic? We're making connections across space, sun to solar wind to planets, and also time. We can make these connections with all the Carrington rotations shown here, but this is just the beginning. We're calling on all of you to provide the rest of the heliospheric mosaic. Just want to point out real quick that in this time is going in this direction with stereo A and SDO maps, and we've got these recurring coronal holes. Some of them are low latitude that join to the polar coronal hole and then break away again. But we've got a lot of data to work with, and it's going to take all of us to do it. So thank you very much for your time, and I can stop sharing now.
Okay, thank you, Ian. Please post your questions on slides. We will talk after the third talk. So now I introduce Rohit Chiber from University of Delaware, NASA Goddard. He will be talking about comparison of Parker Solar Pro first PASIS Global 3D average emission model. So, right, please go ahead.
Thank you.
Yeah.
Are you seeing the full screen presentation?
Yes.
Yes, we do.
All right. So thanks for having me. I'm going to be talking about some work that was recently accepted for the Astrophysical Journal, in which we basically compared our 3D global solar wind model with observations from PSP's first 5 orbits. So just to start off, it's a short talk. So just to motivate the inclusion of turbulence in these kinds of studies, it's well known that the solar wind is turbulent with structure and fluctuations across multiple scales, and the turbulent cascades provides a mechanism to heat the corona, as well as accelerate and heat the solar wind. But in global models of the solar wind, it's not computationally feasible to resolve the small scale fluctuations, right? So the approach we take is we use a global MHD model, but it's coupled to a subgrid scale turbulence model. And what we do here is we compare an ensemble of runs from the model with data that's aggregated from the first 5 PSP orbits. Apart from testing the model in these comparisons, we also want to see if we can extract any kind of long-term radial trends by aggregating data over 2 years of PSP observations that happened during solar minimum. So the approach that we take in our model, it's based on the Reynolds averaging, which basically means that you decompose physical fields into a mean component. So A tilde is a physical field, you decompose it into a mean part and a fluctuating part, where the fluctuation can be of arbitrary amplitude. So what you eventually get is a system of equations that describe the large scale flow. So this is basically your standard 2-fluid MHD with the momentum equation for protons, induction equation, a continuity equation, and 2 equations for electron and proton temperatures. And these set of equations describe the large scale or the mean part of the flow. But these equations are coupled to a set of equations that describes the statistical properties of the turbulence. And I want to emphasize that this is a two-way coupling in that the turbulence provides heating and acceleration for the plasma, for the wind, but in turn, gradients in the large scale fields also drive the turbulence. So I do want to describe the statistical descriptors of turbulence that we have in our model. So first we have the turbulence energy, that's Z squared. It's the sum of the average kinetic and magnetic fluctuation energy. Then we have sigma C, which is the cross helicity. It's the correlation between the velocity and magnetic fluctuations, and it describes the alphenicity of the turbulence. And finally, we have lambda, which is the correlation scale, And this can be associated with the largest turbulent structures in the system. So this model has been developed over the past decade or so, and it's been well tested against 1 AU observations and at larger distances as well. But during the PSP era, we're now able to test this model against observations made much closer to the sun. So as I said, here we look at the first 5 PSP orbits, which gives us coverage of distances from 28 to 200 solar radii. And we use 5 runs, each with a magnetogram corresponding to the appropriate PSP solar encounter. So just to start off with some comparisons of the time series, here I've got orbit from PSP, data from PSP's second orbit. So in this plot on the left, the symbols represent hourly averages of the PSP data, and the red curve represents the result from the model. And the perihelion is represented as this vertical line. So you see that in general, the model matches the radial velocity pretty well. Here I've got the radial magnetic field, again matches well. And this shaded region that you see here, I get this by taking the local turbulence amplitude from the model and adding and subtracting that to the local mean magnetic field. So you get sort of a range of the spread that you expect because of turbulence. I've got the proton density, and while the model misses some of the transient features, you get overall trend. The temperature is actually not bad. On the right, I've got the turbulence properties. And now you can see that the turbulence energy, it increases towards perihelion, but the model result generally skirts sort of the upper envelope of the observations. I've got the correlation scale of the turbulence. And here you're kind of seeing a problem because you generally expect that the correlation scale becomes smaller as you go closer to the sun. And in the model, you're seeing that it goes down by a factor of 2 by the time you get to perihelion. But in the observations, it decreases by almost an order of magnitude. And I won't be able to get into too much detail on this, but we think this might be because of a sampling bias in PSP observations. Because as you go closer to the sun, you're measuring fluctuations parallel to the mean magnetic field. As the mean field becomes more radial closer to the sun, so the turbulence you're measuring is sort of slab-like or parallel turbulence, which we think might have a smaller correlation scale than the 2D turbulence that's mainly described in the model. The cross helicity, again, you see a general agreement. What these sign changes in the cross helicity reflect are basically major heliospheric current sheet crossings by PSP. So as the PSP goes from a region, goes into a region of opposite magnetic polarity, the sign of the cross helicity changes, and it seems like the model does capture some of these heliospheric current sheet crossings as well. So the other 4 orbits generally show a similar level of comparison between the model and the observations. So I won't go into detail there, but what I'll jump ahead to the radial trends that you get by aggregating data from the 5 orbits. So on these plots on the left, I've taken data from the first 5 PSP orbits and just plotted it as a function of heliocentric distance. And that's the hourly averages of the data in the blue squares. And the model result is the red curve. So here now you can see that even though the model doesn't capture some of the transient features, the overall radial trend in the radial velocity is captured pretty well. We've got the radial magnetic field. The proton density and temperature actually look pretty good in terms of the comparisons. The turbulence energy, as I mentioned earlier, it kind of skirts the upper edge of the observations. The correlation scale, again, you see that they're decreasing faster in the observations compared to the model. And the cross helicity looks like a mess here, but it should be a little bit clearer in the plot on the right, where I sort of show the averages of these data on the left. So what I've done in the plot on the right is binned the data on the left into radial bins of size 10 solar radii. And the symbols show the mean value within the bin. And the bars above and below the symbols represent the spread of the data up to 1 standard deviation. So now you can see that there's a pretty good overlap between the symbols, between the model and PSP, but the data, the PSP observations do show more variability than the model. You've got the radial magnetic field. Again, the density and the temperature look pretty good. You got energy, correlation scale, and now what you're seeing in the cross helicity is that in the observations, the cross helicity, which has been sector rectified here, so the sign is always between 0 and 1. So in the cross helicity, you're seeing that it increases as you approach the sun. So the turbulence is basically becoming more alphenic, which is again not surprising. And what you see in the model is that this trend is kind of captured below 100 solar radii, but not so much above 100 solar radii. And we think that this might be because the model is missing sources of shear, which might reduce cross helicity at near the Earth. Right. And I do want to point out that this is, even though you do see some fast wind here, the 95% of the data are slow wind. So this is very much a long-term, 2-year ecliptic plane solar wind kind of ambient solar wind radial trend that you're seeing here. Right. So also got some, yes. So yeah, this is my last slide. I just fit some power laws to the different variables that I've shown here to heliocentric distance. And what you see for the radial and tangential magnetic field is that the power law exponent is actually pretty close to the Parker spiral expectation. And the interesting thing you see in the proton temperature is that you have a power law that's minus 0.8, which is actually pretty close to what you get from Helios measurements, which is 0.9, minus 0.9. And if you compare with what you get from Voyager, then Voyager is minus 0.5. So these Helios and PSP results are kind of suggesting that the heating or the non-adiabatic heating that's happening in the young solar wind is weaker than what you get above 1 AU. And I already sort of discussed the trend in the correlation scale and why that might be because of some sampling bias in PSP measurements. But okay, to wrap up, we're using a two-fluid MHD model which has a subgrid scale component and using it to compare with the near-sun data from PSP. Generally, we see a good agreement between model and data, especially for the radial trends and especially for the bulk flow. We have to be mindful that the turbulence measured by PSP could be biased by sampling parallel to the mean fields. And in the future, we do want to include some higher resolution magnetograms. I think right now we're mainly using Wilcox, and we're also working on including the transition region. Currently, the model starts at the coronal base, and more details on this work can be found in the paper that should appear pretty soon. Right? Thank you.
Okay. Thank you, Rohit. So let's move on to the last talk. Write your questions on Slido so we can discuss later. So we have Alberto Vasquez from the Space Physics and Astronomy Institute from Buenos Aires, Argentina. He will be doing a 3D tomographic reconstruction of 2 of the WHPI objectives about coronal rotation. Lost the number there. Yes, 2219 and 2223. So Alberto, take it.
Yeah, hi. Hello, everybody. Can you see my screen?
Yes.
Okay, and can you see my pointer?
Yes.
Perfect. Okay, so I'm going to show you tomographic reconstructions of 2 WHPI targets. This is a talk prepared by Diego Choveras. He's not with us today because he has some health issues, so I'm stepping in. This is work done in collaboration with friends and colleagues from the University of Michigan, France, Philippe Amia and team. So, you know, as you know, development in 3D MHD models requires validation with data, and we have seen several examples of that today. And in that regard, solar tomography provides validation data for the models at a global scale. And this is what I want to highlight. So like I just said, I'm going to show you results, very recent results for 2 WHPI targets, namely the Total Solar Eclipse Campaign and the PSP Stereo Closest Approach. So I'm going to show you 2 different tomographic products. One is based on AAA EUV images. We have done this with EIT, EUVI, and now AAA. So we use several bands, and we apply what we call differential emission measured tomography. I'm going to talk a little bit about that right now. And then we also do white light tomography, visual light tomography, in this case using LASCO C2 images provided by Philippe Lamy's team. And we also run here a simulation of these periods with the AWESOME model by the University of Michigan. So very briefly, in tomography, you basically use the solar rotation to provide the different views that you need to pose an inversion problem. So originally, tomography was developed for white light, visual light images. So what you see is the K corona, and as you all know, this is provides a diagnostic for the electron density of the corona. And more recently, we have extended the technique to be applied to EUV images. So what we do is to do tomography with different passbands of EUV telescopes. And for each passband, the tomographic product itself, it's a 3-dimensional reconstruction of the emissivity. So once you have 3-dimensional distributions of emissivity in several bands, you can hope to do some kind of DEM measure at each tomographic cell in the computational grid. So this is a technique called DEM tomography. So to complete this, I'm going to show you then how this compares to simulations of the same periods based on the AWESOME model, which addresses coronal heating, as you know, by alpha waves dissipation, and this is part of the space weather modeling framework. What I'm going to show you now is work in progress by Diego Choveras, and this is a series of efforts to carry validation studies of the AWESOME model using, different observational data, and in particular tomographic products. So I put here a couple of references. So very quickly into results, example of results. These are latitude, longitude projections of the tomographic products, in this case, the EUV tomography. So the top 2 panels are showing you electron density maps in latitude and longitude at 2 different heights. When you do EUV tomography, you are recovering the corona in the height range below 1.25, 1.3 solar radii, that is the field of view of the EUV instruments. So you have a map here of electron density derived from tomography at 2 different heights within the tomographic grid, just 2 sample heights, just to show you that this is a true 3-dimensional product. And below them, you have the same maps from the AWESOME simulation. Now, you can see in all the panels these black lines. These black lines are the coronal hole boundaries from the AWESOME model. So, of course, they match exactly well the gradient, the strong gradient of electron density between the streamer belt and the polar coronal holes. In particular, the results I'm showing are just for 22, 23, because I will not have time to show you the 2 rotations here. Now, in the top panels, you see the tomographic reconstruction, and overplotted, the black lines are the same as below. Those are the coronal hole boundaries from the model. As you can see, there is an excellent agreement in general between the structure of the coronal hole boundary and the streamer recovered by the tomography, in the sense that, the highest density region is basically contained within the closed regions. These are maps of temperature, for example, derived also from EUV tomography. you know, the match between the coronal hole boundaries from the models and the structure of the tomography might not be perfect everywhere. And that was the reason of my question to Pete. What we see is that we have done a lot of these reconstructions, and the match between the open-close boundary from the models, of course, and the tomographic reconstructions very sensitively depends on what you use as a boundary condition from the model, for the model. I'm going to show you in a couple of slides similar results for WHI, just so you see a different reconstruction, a different target. And again, for 2223, these are at the top electron density reconstructions of the corona at 2.5 and 4 solar radii as just sample heights within the field of view of LASCO. And below is the results of the ozone model. So, you know, beyond that visual comparison, what you can do is a more quantitative thing by taking, for example, radial profiles of electron density or electron temperature. The top two panels are in the streamer region from the tomographic reconstructions in blue and the ozone model in red. The ozone model has an extended chromosphere region, so it achieves coronal conditions by 1.05 solar radii or so, and you can see the matching density is pretty good. If you go higher up, this is the electron density from the tomographic reconstruction based in LASCO and from the model, and there's a very nice match again. There's a 15% difference, for example, in temperature between the tomographic reconstruction and the model, but this is one of the best matches we have found so far between the model and the reconstructions in tomography. And this is the same for the coronal hole region. Again, we have very nice match in density at the EUV heights, 10, 15% differences of temperature between the two results, model and tomographic reconstructions. And that's where we find the largest difference between the electron density of the model and the tomographic reconstructions based in LASCO, between 2.5 and 6 solar radii. So we can have differences up to a factor of about 2. Still pretty good. Now, before going on, while we were in the sessions this morning, I just put this quick snapshot from a previous paper. This is an example of DMT reconstructions of the previous solar minimum. This is work done by Lloveras. He made a comparison of doing tomographic reconstructions of solar minima from 1996 and 2008, 2009. What I just wanted to show you here, these are all tomographic reconstructions. There is no model here. These are maps of density at two different heights, 1.02 and 1.1 solar radii, and reconstructions of temperature at the two same heights. And again, the black lines are the boundaries of the coronal holes according to a three-dimensional magnetic model. So you can see here, for example, that the match between the structure recovered by tomography and the structure of the coronal holes of the model, it's even better, for example, than in the 2223 case that I just showed you. In this case, I don't recall exactly which synoptic magnetograms we use. For 2223, we use adapt gong. And in this case, I really need to look back into the paper. It probably was gong maps.
1 minute.
And just to show, thank you. Just to show you another example, this is a tomographic map, for example, of electron density at one particular height and tomographic temperature at one particular height for WHI. And again, the black lines, the thick black lines, are the boundaries of the coronal holes according to the magnetic model. As you can see, not only the large scale structure match very well, but sometimes you have very small features, like, for example, this enhancement of density here and temperature, that is basically nice match between the tomographic reconstruction and the model. So depending on which reconstruction you talk about, which rotation you focus, you might have larger or smaller differences between the model and the tomographic reconstructions. What we usually do is we take, for example, real images that we use for the reconstructions. Here you have a 193 AIA image for 2223. This is the same image top and below. And the right panels are the tomographic synthetic image and the awesome model synthetic image. And here you have the histograms of ratios of intensities. So of course, the model is doing pretty well, but of course, the tomographic reconstruction is able to reproduce finer details. Here's an example for a LASCO image. So you have here a real LASCO image, is the same at the top and the bottom. And here on the right side, you have the synthetic image from the tomography and from the model. And here you have the ratios of intensities, you know, the synthetic image over the real data for tomography and for the model. So this is just a final slide with a few conclusions. This is uploaded so you can read it. What I want to stress now is what we are sharing with you guys on through HSO Connect. It's a very simple Google Drive where we have put the electron density and electron temperature reconstruction based on AIA data below 1.25 solar radii, and the electron density based on LASCO images reconstructed between 2.5 and 6 solar radii. And there's a small self-explanatory and standalone ideal code that can read these data cubes for you. It's pretty self-explanatory, but you can write to us. So hopefully this will be of interest for some of you. And I think that's all. Thank you very much.
Thank you, Alberto. Very nice now having the data available to everybody to take a look and discuss further. So let's start the discussion. Heather was taking in charge of the Slido. I don't know if you, Heather, will share it, or Kelvin. And
yeah, I think we see if we can get them on. Zubar Shaikh, if you can unmute.
Needs to raise his hand and keep his hand up.
Okay. Thank you. Yeah, you need to raise your hand and we'll, okay, he's got his hand, or they got their hand raised.
Hello. I'm audible?
Question?
Yes.
Yeah, actually, it was a nice presentation. My question is, as in last presentation, he said that he wanted to connect what is happening on the matrosphere, like geomagnetic storm, to the sun. So the basic question is, we know that CAR induces geomagnetic storms and CME geomagnetic storms, we understood well. There are a lot of studies happening so far. But what are how we can understand the effect of, for example, high-speed streamers from the sun to the matrosphere? Because in between there are a lot of interaction can take place, and we do not have the facility from which we can trace the high-speed streamer from the surface of the sun to the L1 position. So how do we do that? What should
I think this one is for Ian, and yeah, and clearly, like, dynamic interactions that happen in the interim. You know, how do you just distinguish what has happened in the interim from what was originally from the sun as part of this? Okay. So Ian.
Yeah, I guess one of my questions is, to bounce it back at you, is what are you thinking about in terms of the sun that is outside of CMEs and CIRs, which are high-speed streams, but also I haven't really studied the magnetosphere, so Rachel or someone else might be a better person to answer your question. Sorry about that.
If I can add something, this is a very good question, because exactly what's happening when you don't have any of these CMEs or CIRs, there is still an interaction. So the question is that quiet or non-active sun, how is it affecting the magnetosphere? I think there is something going on, but exactly what, I'm not sure.
Thank you. Thank you, Carlos.
Any other thoughts?
one more point I wanted to add in this direction. Like there are many there are some observations in the literature available which says that the ghost CME, they used to say it is a ghost CME because LASCO observation, LASCO cannot detect or cannot observe this faint CME which used to emit from the sun. So, and literature says that it can affect the matrosphere, planetary matrosphere. It can be from the inner heliosphere to the outer heliosphere. So, how do we connect those phenomena with that with matospheric planetary point of view? I can say that because LASCO sensitivity is not that much strong, which can observe such faint CMEs or faint phenomena which is happening on the sun. Thank you.
Okay, so let's move on to the next question.
Okay. I had one for Rohit. You mentioned that you didn't observe a lot of fast wind, but I was wondering if you had expected to see more fast wind based on where the spacecraft mapped on the sun. So, so is it all that you just weren't in the right place at the right time, or is it that maybe the solar wind hadn't sped up not much at that point?
I think it's definitely the case that I think PSP observed fast wind mainly during the first solar encounter. And during that time, it was connected to a low latitude coronal hole. So most of the fast winds that we see in the first 5 orbits aggregated comes from the first encounter. I think in the orbits 2 to 5, it was just not, there wasn't any low-lying coronal hole that PSP was mapping to, which could have produced the fast wind. So I think it's definitely a function of where the spacecraft is mapping to. As far as the model goes, I think, so we've actually tried to map the model back, the PSP location back to the solar surface that you have in the model. And I think this is because we're using lower resolution magnetograms. We just don't map back to the low-lying coronal hole. It's just not there at our coronal base. I think, and other models that I've seen, most of them do not reproduce that fast wind patch that PSP saw during the first encounter, except I think the PSI model, they, if I remember correctly, their prediction paper showed a fast wind measurements during the second half of the first PSP encounter. So this seems to be the low-lying coronal holes that, I don't know if how well our MSE models do in mapping back to them when they're actually present on the sun.
Okay, well, thank you.
Sorry, yeah, before we go ahead, Zubair, I think pay attention to the last session on Friday, this working group, because basically it's that the effects of non-active sun on planetary atmospheres and magnetospheres. So we might learn something there.
Okay, so we have a question from Sarah Gibson for Alberto. So we can let her do that.
Yeah. Alberto, yeah, basically, as you know, we've had conversations yesterday during the data and modeling about the kind of the synergies and which models you have information and what you compare to. And I sort of want to plant the seed on everybody's mind who's showing material to think that we've got a very broad group on this online and at WHPI. What's your ideal? What do you want to look at? What do you want to compare to?
Well, of course, the obvious first comparison are the direct products of tomography, which are electron density and temperature at EUV heights and electron density higher up at the LASCO C2 field of view, for example. I should mention that, if you guys are interested, in my talk, I just show you the series of comparisons that we're making with the OSOM model as a validation tool for the OSOM model. So probably I would like to invert. I mean, your question is just fine. I just would like to offer the possibility of the tomographic reconstructions as a validation tool for the models. Like I just showed you, you can have higher or lower degree of match between the structures you see in the tomographic reconstructions and the models. But I think then it's very important to compare from both synthetic images, for example, and see which images match better the data. So, in a way to assess how reliable are those reconstructions. Tomographic reconstructions have their limitations. Earlier today, I think it was Pete who said, models are not perfect, but they are really useful, or many times they're very useful. Tomographic reconstructions are not perfect. They have their limitations, of course, but they're really very useful. So I would say electron density, electron temperature within the UV field of view, and electron density higher up within the LASCO C2 field of view. And I want to highlight, for example, the LASCO C2 legacy site built by Philippe Lamy and collaborators, on which they have put an enormous amount of material, in particular 3D tomographic reconstructions of the electron density. So I think this is very valuable for model development. Let me mention something else. We are currently working in a new tomographic product derived from EUV tomography, which are estimates, two-dimensional maps at the coronal base of coronal heating rate. That's work in progress. We have some preliminary results published in APJ 2 or 3 years ago by Cecilia McCormack and collaborators. And we are working with Diego on new results on that front. So, comparing with heating rates from models would be interesting too.
Okay, we have another question from Dave Hathaway. Let's see if they can give Dave permission to unmute.
Raise your hand, Dave. Yeah.
Okay, he's got his hand raised. Okay, see if you can unmute, Dave.
There we go. I think that's it. This is more a comment than a question, and Pete Riley brought this up a little bit, that the typical synoptic maps that you get are maps in time, not longitude. In particular, at high latitudes where the rotation period is 34 days, in a 27-day period, you only get about 280 degrees of longitude at those latitudes. So I'm assuming that most people know that if you're doing some sort of mapping of the surface field into the heliosphere, you need a synchronic map. Maps like what are provided by ADAPT and other people that do surface flux transport to move the flux around appropriately and to capture all longitudes at all latitudes. So it's just a comment.
Okay. I think next up, Sarah Gibson wanted to show some related mosaic overview work that she has.
Yeah, it's not overview work. It's really just to get you interested in communicating your interest in working on an overview paper for WHPI. So let me go ahead and share my screen. So for all of the, since this is the mosaic session, it seems like a good place to introduce this concept. Do you guys see a spreadsheet?
Yes.
Okay, great. So for all of the whole sun month of the WHPI, we had the challenge of how do you compare information from all these different regimes, from sun, solar, wind, planets, and then over different timescales. There are all sorts of subtleties involved, including what Dave was just saying about how your Carrington map is actually assuming a rigid rotation, which the sun doesn't have, and what does that mean in terms of time? There's subtleties about how you map back solar wind to their sources, et cetera. But in general, the question of how do you just present a snapshot of what's going on? And what we did with the whole heliosphere interval was we did model and observations. And we compared, for example, the magnetograms to helioseismic flows in the subsurface. And we kind of moved out in the atmosphere, coronal hole boundaries, as observed from, like, as Ian was talking about, versus the open field foot points. And we saw a lot of that with Janet. And then moving out into the observations in extreme ultraviolet and soft X-ray, the white light going up in height. And then when you get out to solar wind, you can start doing things where you plot versus time on plots that are comparable to what you're seeing back at the sun. You can do more complicated map backing, et cetera. It's a whole thing. And for WHPI, we'd like to do something similar. It's more challenging. There's more information. I think we're going to have to break it down. So maybe we look at 1 or 2 solar rotations in the manner that was done for whole sun month, and then also consider the long-term evolution over the year. I've started a spreadsheet. If I can go back to it. There we go. And I'll make this available to anybody who's interested in participating in this. And basically, we want to identify 1 or more people in each regime. And we started gathering what possible things we might want. The observations of the sun and the solar wind and other planets. The planets are here, forward modeling of the sort that we also saw Alberto doing. Derived data products that one makes, well, actually that's in the density and the temperature, which then can get forward modeled back into something that's comparable to the observations. And we've just started fleshing this out with some links. So I just wanted to advertise this, and we'll have more opportunities. You can direct message or email me, and I can give you the link to this. And we're trying to identify people who are interested in being involved in this overview paper that would do our best to try to look at all the observations from the interior of the sun out to the outer heliosphere for a very localized specific time during solar minimum. So that's pretty much that. We've started putting some names in, but they are not the only ones. Don't be discouraged if you see somebody else's name in an area that you are. We need more than 1 people involved. Does anybody have any questions about that?
Okay.
And actually, Pete, can we have a comment really quick about special issues for a journal? If you can briefly mention it, we can we're going to circle back to this on Friday for sure, but we are trying to organize some publications. Is Pete here and able to comment on that?
Yes, Pete is a co-host. He should be able to unmute. He might be away from the computer.
Okay, well, in the interim, we do have another question. We have one from Claudia Nicoli. Let's see if
raise your hand. Yes.
Yeah, raise your hand and we can see if you can unmute. Okay, the hand is raised.
Hi, thank you. It was a very nice talk. I have many questions about these studies on features, different features on solar wind and coronal holes, because I'm researching low latitude ionosphere. And so we are studying the impact of solar wind on the geomagnetic storms. And are you seeing me? I think that I opened my camera.
Yes, yes,
okay.
We can see you.
Okay, we are especially interested in the impact of solar wind, the CIR, on the geomagnetic storms and the low latitude ionosphere. And I'd like to know which is the most important feature or characteristics of the solar wind and coronal holes we could track, we could perhaps revealed by tomography for application in this space weather prediction and forecast. And they are impacting ionosphere.
Are you talking about tomography in the solar wind or tomography in like ionosphere?
No, not the ionosphere, but
like the source from the solar wind.
Yes,
like,
the idea
like
is use all these techniques to track or to know how which is the most important feature observed in solar wind or coronal holes.
Yeah.
In for space weather prediction and forecast.
Yeah. Okay. Do we have any takers from the previous speakers?
Well, I can make a quick comment. Thanks, Claudia. We don't have much experience yet on that. I mean, we have been because we work, like in the base of the corona, but of course that's the source region for everything related to space weather. So it's a very interesting question. In the current analysis that Diego is doing in collaboration with the University of Michigan, we are doing for the first time, I just show you a few profiles of electron density and electron temperature as a function of height, but those are really very preliminary. What Diego is doing right now is tracing along the field lines of the model the tomographic results and relating those quantities with the terminal properties of the model at 1AU. But that's a very new thing that we are doing. So we are very interested in actually the question that you just posed. I guess, for example, looking for, how wind speed of the model, terminal wind speed, correlates with the tomographic maps at the low corona is very interesting. We are just starting to do this kind of comparison.
Yeah, I could comment a little bit. This is Heather. So if you just take the KP index, for instance, it correlates extremely well with the solar wind speed and the density. So the higher the density in the solar wind and the higher the speed, no matter whether it's a CME or whatever structure it is, the faster and the more dense the solar wind is, the higher the KP index will be. So if you're talking about tracking structures from the sun, it's going to be easiest to track the bright features that stand out. So the CIRs are going to be easier to track than the fast wind, which is less dense and it'll be less bright. But the lower down you can go into that, looking at the fainter features, the more likely you would be able to do the tracking from the optical images. And so, so that some people from the punch team might want to talk about like how like dim a feature, like how low a density structure would they be able to track to get the speed on some fainter structures. But there is some hope that that progress can be made on that.
Mm-hmm. Okay, thank you.
Okay. Any other question, comments? We have a couple of more minutes.
Yeah, I wasn't seeing any new questions.
One. If not, we can start an early break. Last chance.
Yeah, people might want an early break.
Yeah.
To break, yeah.
Sounds good. Okay. Thank you to the speakers. Thank you for the questions. And let's hang out for a little bit more than 15 minutes, and then let's get back and with more exciting sessions. Okay, thank you.
So please come back by 55 minutes after the hour. Thank you.
Thank you.